Hey everyone, welcome back to Particle Systems, Part 2. Last time we talked about how to simulate smoke and bouncing balls. We used Euler integration to perform the simulation. One parameter you can play with is the step size. The step size affects the accuracy of the simulation. In other words, how well the blue region approximates the area under the curve. The pink areas are where the approximation is too small. The orange areas are where it's too big. A larger step size results in a worse approximation, more pink and orange. A smaller step size provides more accuracy. A step size of 1 over 300 works pretty well for this simulation. That's 10 updates per frame of video. The ball on the right gets only 1 update per frame. You can see that the motion is different. Let's see that again. The right ball hits later. It's lost some velocity. Why does that happen? Well, let's plot the correct velocity of the falling ball, which increases linearly with time. Notice that our Euler approximation consistently underestimates the area under the curve. It's missing these pink areas, so the estimated velocity will be lower than the real velocity. And that's why the right ball moves slightly slower. And if we keep going, the right ball never stops bouncing. That's another common artifact of having too large a step size. Great, now let's have some fun. Let's add another wall on the right to create a basket in the corner. And we want our ball to land there. It's harder than it looks. It bounced right out. We need to figure out what direction to throw the ball so that it lands in the basket. Like this. To do this, you can think of the ball as tracing a trajectory. This lets you see the entire trajectory all at once. Pretty cool, huh? We'll simplify by showing just the curve that the center of the ball traces. Now you can try a bunch of different initial velocities and see how the curve changes. So if we continuously vary the initial velocities like this, the trajectory changes like this. That went by pretty fast, so I'll play it again and pause when it gets interesting. Here's the first landing. Here's the corresponding animation. It bounced twice on the ground before landing in the basket. Let's advance to another successful landing. Here it bounces a few times on the block. And here's one more. It's the closest thing to a straight shot. We can also model springs with particle systems. If you stretch a spring to length x, it creates a force in the opposite direction with this equation. K of S encodes how stiff the spring is. More generally, the force is proportional to the displacement away from the rest length r. And we can have other forces acting on the particle, like gravity. Another common force is drag, which is proportional to velocity. The faster something moves, the more the drag force tries to slow it down. The total force is just the sum of all the forces acting on the particle. But wait a minute, how do we apply a force to a particle? We've only talked about accelerations and velocities so far, not forces. Newton's second law tells us how to convert forces to accelerations. You just divide by the particle's mass. In summary, here's how a particle system works. In each time step, you start by adding up all of the forces acting on each particle. That gives you a vector f of forces. And don't forget to initialize f to 0. Then you divide each particle's total force by its mass, yielding a vector of accelerations. Step 3 is to update the position of each particle, and in step 4, you update the velocities. You then repeat over and over again for each time step. Let's try it out for a ball and a spring with these parameters. It's a bit like a springy pendulum. We can make it move more like a real pendulum by making the spring a lot stiffer. But hey, what's going on here? The simulation is unstable. The problem is that Euler's method takes 2 time steps after a force is applied to affect a particle's position. This delay can cause small errors. In the case of a stiff spring, even a tiny overshoot can create an enormous counterforce. That's the cause of the instability you saw in the last video. You can make springs work better just by swapping the order of the velocity and position updates. Now the position uses the new updated velocity instead of the old one from the previous time step. This variant is called Symplectic Euler, and it's a lot more stable. There are many other types of integration methods to choose from. You can create all sorts of fun things with particle systems, including a pinball machine. I hope you enjoyed this video on particle systems.